All right, folks, back at it. We're here for lecture number 2. I got the same shirt on, so you can tell it's not a different day. Just keeping this going. All right. Hope you're ready. I'm ready. Okay. Let's do it. Okay, so let's just pick up right where we left off, shall we? We're going to get into now molecular partition functions and more on this notion of populations or populations of state. And molecular partition functions are useful equations that actually allow us to calculate the population of a state. So we recall the Boltzmann distribution, and I'm going to just write it in a slightly different way than I did last time. So I'm going to write in I, so number of molecules in state I over in total, so over the total number of molecules. And so now I'm going to write that as exponential negative, and I'm going to write negative beta times EI. Okay, I'm actually going to make this pen a little bit thinner. There we go. Where beta is 1 divided by kBt. Okay, so you remember last time we said it was E raised to the negative energy divided by kBt. Okay, and there's definitely some exponential algebraic tricks at play here. Okay, and so that's my number of molecules in state I. And if I want to divide this by the total number of molecules, then I'm going to say that's the sum of all of these exponential contributions, okay, where now I'm going to say that's beta times capital E. And here in this case, if I take, the sum of all populations I times their respective energies, that's going to give me the total energy E. Okay? And of course, right, the sum of all populations of NI will equal in total. All right? So you can see that this is really still the same Boltzmann equation we wrote last time. It's just slightly different and using a little bit of algebra as a matter of convenience. Okay, so now I'm going to write here the molecular partition function, which is going to be based off of this Boltzmann distribution. Okay, and I'm going to write that as little p sub I. And so this p of I is the fractional population of state I. So it's basically the same thing as this, right? Like so, or really you could think of them as a decimal percentage, if you will, not a fractional, okay? And I'm going to say that equals exp bracket negative beta times energy, and I'm going to say divided by Q, okay? Where Q is my actual partition function. All right, Q is the partition function. And so that Q equals the sum of all of those states, of course, raised to this exponential equation. Okay? So if the states have the same degeneracy, and so notice over here a degenerate state, 2 or more states having the same energy level. So think of a p orbital, for example. And so I'll give you, so in that example, right, if I have like the, let's say the 2p energy level, we really recognize it goes 1, 2, 3. So that's got 3 equivalent degenerate states. Or like a d orbital has 5, or an f orbital has 7. Okay? So that's what we mean by degeneracy. So if there are equivalent degenerate states, I'm going to write that as Q equals the sum, and I'm going to just write a different letter here to signify it's just slightly different, capital I. So I'm going to say now that's G sub I, Q and G, okay? So that the G is my degeneracy term, and then of course that's still going to be times this exponential, okay? So basically, if there are degenerate terms, let's see, degeneracy, then we can account for those degenerate terms when we're summing up this total population, okay? So we're not really going to get into the nitty-gritty details of degeneracy really until like 362 with spectroscopy, but it's a good time to introduce this concept, okay? So now let's apply this partition function to one of our energy levels, okay? So let's consider a system with linearly spaced energy levels, and that turns out to be the vibrational modes of energy have linear spaced energy levels. And I'm labeling those as 0, E2, E3, E4, E, which you could still think of as like level 1, level 2, level 3, level 4, level 5, etc. But now I'm putting values for their energy, okay? And so this ground state, I'm giving it a 0 value, which is not to say that it doesn't have any energy at that state. It has its base thermal energy given to us by 298 Kelvin, the kinetic energy available. But to go to the next energy level, it has to be supplied the value of E, right? So I can go from 0 to E, E to 2E, E to 3E, right? And they're all spaced by levels of E, okay? So we could think of these also, this 0 right here, as the vibrational number, which as it turns out also gets a Greek letter nu. So don't let that confuse you. There's too many Greek letters, or not enough Greek letters rather. So I will say that the energy of any of these states I is going to be given by this vibrational quantum number 0. And really I screwed this up. I should have said this is 0. And actually I think, look at this. Do I have an eraser? Oh yeah. I told you I'm learning as I go here, folks, on how to do this new technology. Okay, so really I'm going to give that a 0 to make this more correct for vibrational energy levels. Okay, so I'm going to say then any of those energy levels equals nu I, which is this letter here, and really this, yes, okay, now we're cooking. This is this value that I'm working on right here. Haha, all right. So now I'm going to say this is times then E, right? So E, 2E, 3E, 4E has that value, right? Depending on which level we're talking about. So for example, if I wrote E1, that would be quantum number 1 times E, okay? Or E2 would be 2E, okay, etc. So now let's build up the partition function for this system. So I'll start by writing Q equals. And we know our partition functions have this form. Let me just back up one slide. It has this form, this exponential to the negative beta times this value of E, right? So if I move forward here, so the first one that I want to sum up is this level 0, which is going to be E raised to the 0 power, right? 0 times E. And anything raised to the 0 power is 1. So the very first term in my partition function is numero uno 1, okay? Because it ended up being E raised to the 0 power. So now the next term, okay, is going to be, and I just for convenience, I'm going to switch to writing that because it's not too bad. So E to the negative beta, and then it's going to be this value of 1 times this value of E. So I'm just going to write that as E right there, okay? Plus, and then my second term is going to be E to the negative 2 beta E, plus the third term is E to the negative 3 beta E, and so on and so forth, right? We can see that that's how we're carrying out that sum. We're summing it through all of those states in the partition function. So those of you that are good at math will recognize this as a Mclaren series expansion. Maybe you did, maybe you didn't. Hopefully you did. But it's been a long summer, right? So I'll forgive you if you didn't recognize that right away. Okay, so in this Mclaren series expansion, I can write this in a simpler way. I can write this as Q, the partition function, is 1 divided by 1 minus e to the negative beta e, right there. Okay? And so this would be a partition function for a system with linearly spaced energy levels. So for the electronic levels or the rotational levels, we should not expect this form of the partition function because it doesn't have evenly spaced energy levels. And this is really the only partition function I'm going to play with in this class. When we get into 362, we'll get much more in depth with all of those other partition functions. So as I said in the previous lecture, this is kind of like a crash course introduction to statistical mechanics. Okay, so now let's see, if we then go and expand this, suppose that I want to know the population of state I, any state I, okay? So I remember I can write that as e to the negative beta, and I'm just going to put in this general term there, so we note that that can be connected to any one of these energy levels, right? Which is, of course, then divided by the total partition function Q, all right? And then now, if we consider that we're talking about a system that's linearly spaced, and we do a little bit of algebra, right? Plug this thing into Q, okay? And make substitutions, then what we get, okay, I'm not gonna show the steps explicitly, and anytime I skip some algebra steps, it's not my intent to, like, you know, make you memorize how to do the algebra unless I tell you I want you to be able to do this. So for now, I'm not too worried about it. I'm just gonna give you the result, okay? So when I simplify this, when I plug this in and make the simplifications, I can get the following, okay? I get 1 minus e to the negative beta e, big capital E, okay, times e to the negative beta, and then I'm going to use this little lowercase eta e. Because now what that's going to allow me to do is whatever state I want to know, if I want to know about the second, third, or fourth state, then I can plug that value into here. But this remains as e to the negative beta eta e. Okay, beta e, excuse me. All right?